Algebra 1 skills number 46, graphs of exponential functions. Let's study those terms. We're going to review exponential a little bit here. But first, what is a graph? A graph is simply a picture of all solutions. It just shows you all the places where if you put the numbers or the order pairs that work into x and y, you get a true statement. For exponentials, remember it's going to have this basic appearance. This is on a lot of formula sheets where b is your base and a is just some real number. The base can't be negative, 0, or 1, and we have a variable exponent. Okay, so again, there's that summary. Okay, there may be other numbers added or subtracted into and out of the exponent, but we want our exponent to be linear, so we don't want x squared up here, for example. Is it exponential? Okay, so just yes, no questions. And sure, this first one is perfectly exponential because, again, your base is appropriate. It's not a native number, 0 or 1. You have a variable in the exponent. There's a -4, but that's okay. It's not squared or anything like that. So yeah, that's fine. And this one's no good because you have to have a variable in the exponent. The base is an unknown variable. This is actually a quadratic function. So no, that's not exponential. You don't have a variable in the exponent. Okay, a third example. Again, this one's perfectly fine. Your base is below 1, but that's fine. It's not 1, it's not 0, it's not negative. You have a variable in the exponent, so no problem there. Okay, and then finally, here, it does have a variable in the exponent, but you don't want a base of 1. 1, 0, or negative is what we must avoid. Okay, now we have this concept of growth versus decay, which is very important when you're graphing. Again, there's the exponential base. If the base is bigger than 1, remember it can't be 1, but if it's bigger than 1, it's growth. If it's between 0 and 1, it's decay. Okay, remember it can't be 0, can't be 1, can't be negative. We do want to make sure x is positive. That's not going to be much of an issue in Algebra 1, but we want to make sure that's positive and use our exponent rules if it's not. So some examples, this base is between 0 and 1, so it's a decay. This base is larger than 1, and a quick note here, the number in front is irrelevant when it comes to determining growth versus decay, so we don't care about this. We're only looking at the base. It says growth. A parent growth graph looks like this. All right, so here's the basic appearance. You're very flat on one side and steep on the other. There's a line called an asymptote that we're going to talk about in just a minute that the line approaches but does not cross. Okay, so again, when you sit flat on one side and it grows, you read a graph like a book left to right, so it's growing as you go to the right. The decay graph looks just like it, it's just flipped. You're actually flat on the right-hand side and steep on the left, but we're going down. We're losing value here because, again, you read a graph to the right. Asymptote we mentioned is a line that a graph approaches more and more closely but does not cross, at least as it approaches, as you go off the screen, it does not cross it. Okay, so how do we graph these? How do we get a rough graph? Of course, you can always go to a graphing utility like Desmos, but the test, this is going to want to make sure you understand the basic appearance of it and features of it. Okay, so if you're having to graph some by hand, the first thing you want to do is place the asymptote. It's going to match the vertical shift, which we'll review that with 3 examples, but it's the big number that you're adding or subtracting. That's where the asymptote is. You're not going to cross that line. You want to make sure if it's growth or decay, because remember the graphs look different. Growth goes up to the right, decay goes down to the right. And then be mindful of transformations, like you might shift it, you might stretch it, etc., reflect it. Here's an example, graph until the domain range. Okay, so here, again, this is exponential because you have a variable in the exponent. It's a good base of 2. So I'm going to go ahead and put the graph up, and let's talk about it. First, the asymptote is this vertical shift up for us, the purple dashed line. Note that it's a growth, okay, because the base is bigger than 1. So it goes up to the right. Now, another thing you'll see people do is find the y-intercept. Remember, the y-intercept can be found by putting 0 in for x. 2 to the 0 power is 1, 1 plus 4 is 5. So if you want to get pretty specific with it, you might want to get the y-intercept. But in general, if you know that it's a growth and you know where the asymptote is, you're in pretty good shape when it comes to graphing by hand. Now, domain and range, remember domain is all values going left to right, and range is all values going down to up. Well, the domain's all real numbers. It goes left forever. Remember, it's getting close to that purple line, but it's going to continue to get close and close to that purple line forever to the left. And also, though it's more going up, it's still going to the right. So it's going to go left forever, right forever. We call that all real numbers. The range, however, has a boundary on the low side. It never crosses the 4. So we say our range values are all values bigger than 4. Not 4, but all values bigger than 4. Okay? Let's get 2 more examples. A second example, same instructions. This time we have a decay because the base is between 0 and 1. Notice also we have a -5 right here, which is going to affect it. We still have this vertical shift. Here's what the graph looks like. Again, the first thing, if you're graphing by hand, you probably want to put this dashed line first to give it structure, and it's at -1. Okay, notice also it's the decay graph is going down to the right. Notice one more thing here. It's noticeably shifted right compared to example 1. That's because you're subtracting 5 on the inside. If you remember your graph transformations, the subtract on the inside is a shift to the right. If you were to find the y-intercept and put a 0 in here, you'll find it to be up here higher than 5. I didn't actually compute that, but if you want to get a little more specific, you could do that. Now, the domain, again, is all real numbers because you're going left forever, right forever. The range, again, has a boundary here at -1, and so it's all values above -1 because the range is down to up, domain's left to right. Let's get a third example. Okay, graph, tell the domain and range. This time we have a reflection. Okay, that's going to cause it to turn upside down. Notice also you're not adding anything out here, so it's going to have the x-axis as an asymptote. Okay, so you see that here, the x-axis is an asymptote. You don't have any kind of vertical shift. Now you do have a slight horizontal shift to the left. And notice that this was a growth. If it were a growth, it'd be going up like this. But because it got reflected, it looks more like a waterfall. It's going kind of down to the right because of the flip. Our domain is still all real numbers because you're still going left forever, right forever. But our range this time has a boundary on the high side. So we say y less than 0. All values less than 0. So a little bit about exponential graphs.